The newest measurements of the interstellar object 3I Atlas have revealed something scientists were not expecting. When astronomers analyzed the gas surrounding the object, they discovered extremely unusual isotope ratios. These ratios act like chemical fingerprints that reveal where and when a piece of matter formed. In this case, the fingerprints do not match anything commonly seen in our solar system. The gas released from 3I Atlas contains an unusually high amount of deuterium compared to normal hydrogen, along with strange ratios of carbon and nitrogen isotopes. The numbers are so different that they suggest the material may have formed in an environment far colder and far older than most planetary systems we know. The deuterium to hydrogen ratio is the most striking of these findings. Deuterium is a heavier version of hydrogen that contains an extra neutron. In most parts of the solar system, the ratio of deuterium to hydrogen stays within a relatively narrow range. Earth's oceans have one value. Comets from the outer solar system have slightly higher values. But the gas measured around 3I Atlas appears to contain a deuterium to hydrogen ratio more than 10 times higher than what astronomers typically observe. Such a large difference immediately suggests that the object formed in extremely cold conditions, likely far below -200 degrees Celsius. Temperatures this low allow deuterium to accumulate in water ice over long periods of time. Carbon isotopes in the gas show another surprise. Carbon exists in different forms, mainly carbon-12 and carbon-13. In most stars and planetary systems, the ratio between these two stays fairly stable because they are produced by the same processes inside stars. But measurements from 3I Atlas show a much higher ratio than what astronomers usually see in material from our solar system. This suggests the carbon in the object may have formed in a different kind of stellar environment, possibly much earlier in the Milky Way's history. Nitrogen isotopes add another clue. Nitrogen commonly appears as nitrogen-14 and nitrogen-15. The ratio detected in the gas around 3I Atlas does not match the nitrogen found in Earth's atmosphere, meteorites, or known comets. When scientists combine this unusual nitrogen signature with the strange carbon and hydrogen ratios, they end up with a chemical pattern that does not fit well with standard models of planetary formation. Some researchers think these isotope clues mean that 3I Atlas formed in a very ancient part of the galaxy. Early stars contained fewer heavy elements than modern stars. If a planetary system formed around one of those early stars, icy bodies from that system could preserve chemical signatures from a time when the Milky Way was much younger. In that case, 3I Atlas might be a fragment from a planetary system that formed 10 to 12 billion years ago and was later thrown into interstellar space. However, this idea raises another problem. Early stars had fewer heavy elements available to form solid objects. Yet the number of interstellar objects passing through our solar system suggests that large amounts of material must have been ejected from many star systems over time. When scientists estimate how much mass would be needed to produce that many objects, the numbers appear very large. This means the isotope data may point to an origin that current models of galactic chemistry struggle to explain. The strange isotope data is only the latest chapter in the story of 3I Atlas. Since the object was first detected by astronomers using the Atlas Sky Survey system, it has attracted attention for several unusual characteristics. Astrophysicist Avi Loeb has been one of the most outspoken researchers studying the object. Over time, he compiled a list of 18 different anomalies associated with 3I Atlas. Several of the anomalies fall into a category that could be described as geometric coincidences. One of the first things astronomers noticed about 3I Atlas was that its orbit appears surprisingly aligned with the general plane of the solar system. Most planets orbit the Sun in roughly the same flat disk. Interstellar objects, however, are expected to arrive from random directions. The fact that this object's trajectory lies relatively close to that plane is therefore somewhat unusual, although not impossible. The path of 3I Atlas also brings it near the orbital region of Jupiter, the largest planet in the solar system. Jupiter possesses an enormous gravitational influence that extends far into space. Astronomers measure this region using something called the Hill sphere, the area where the planet's gravity dominates over the Sun's. The projected path of the object appears to pass near this gravitational zone. While this could easily be a coincidence, it means that Jupiter's gravity will play an important role in shaping the object's motion as it continues its journey. Another curious alignment occurs with respect to Earth and the Sun. At one point during its approach, the geometry of the orbit placed 3I Atlas nearly along the line connecting Earth and the Sun. During that time, a feature known as an anti-tail, a structure made of dust particles pushed by solar radiation, appeared to point roughly toward Earth. Antitails are not unheard of in comets, but the geometry required to see them clearly from Earth is relatively rare. The arrival direction of the object has also drawn attention because it lies not far from the region of the sky associated with the famous WOW signal detected by radio astronomers in 1977. That signal was a brief burst of radio energy that has never been fully explained. The proximity of the two directions may simply be chance, but it has added another layer of intrigue to the discussion surrounding 3I Atlas. Observations of the object's jets provide another geometric puzzle. As the Sun heats the surface of icy bodies, gas can escape through cracks or vents, producing narrow streams of material known as jets. Images of 3I Atlas suggest that some of these jets point roughly toward the Sun. Even more intriguing, similar structures appear both before and after the object passes its closest point to the Sun, creating a kind of mirror symmetry in the pattern of outgassing. In addition to geometry, the composition of the gas released by 3I Atlas has raised questions. Spectroscopic studies allow astronomers to identify the elements present in the cloud of material surrounding the nucleus. In this case, some measurements suggest an unusual abundance of nickel relative to iron. Most comets and asteroids contain these elements in more balanced proportions because they formed from the same mixture of material in the early solar system. A higher nickel-to-iron ratio could indicate that the object originated in a different chemical environment. The overall mixture of gases also appears somewhat different from what scientists normally expect in comets. Water vapor is usually the dominant component of cometary outgassing when an icy body approaches the Sun. But some observations of 3I Atlas suggest that carbon dioxide and other carbon-bearing molecules may play a larger role than water in driving the activity. This does not mean the object contains no water, but the balance between different gases may not match the pattern seen in many familiar comets. Dust structures around the object also behave in interesting ways. The anti-tail observed from Earth appears unusually narrow and extended. Dust particles released from the surface interact with solar radiation and the solar wind, sometimes producing complex patterns. The exact shape of these features depends on particle size, velocity, and the direction of the comet's motion. The dust geometry around 3I Atlas has therefore become another topic of detailed study. Beyond chemistry and geometry, astronomers have also noticed several unusual physical properties. Estimates of the size of the object suggest that its nucleus may be relatively large compared with earlier interstellar visitors. Its velocity through the solar system is also quite high, consistent with an object that originated far outside the Sun's gravitational influence. These characteristics alone do not make it extraordinary, but they add to the growing list of features researchers are examining. One particularly interesting observation involves the polarization of light reflected from the object's dust cloud. Polarization occurs when light waves vibrate more strongly in one direction than another. By measuring polarization, scientists can learn about the shapes and sizes of dust particles in the cloud. Observations of 3I Atlas indicate unusually strong polarization signals compared with typical comets, suggesting that the dust grains may have different structures or compositions. Brightness changes near the Sun have also drawn attention. As icy bodies approach the Sun, they usually brighten gradually as more material begins to vaporize. But 3I Atlas appeared to brighten quite rapidly over a short period of time. Rapid changes like this can occur when fresh ice is suddenly exposed or when jets begin to erupt from the surface. The exact cause remains uncertain, but it has become another feature that astronomers are monitoring closely. Measurements of the object's motion indicate slight deviations from the path expected from gravity alone. This effect, known as non-gravitational acceleration, is common in comets because jets of escaping gas can act like tiny rocket engines. When gas streams out in one direction, it produces a small push in the opposite direction. In most comets, these forces are relatively easy to model. For 3I Atlas, however, scientists are still working to determine exactly how the outgassing influences its trajectory. All of these observations are taking on new importance as the object approaches a key moment in its journey. On March 16th, 3I Atlas will make a relatively close passage near Jupiter. Jupiter's immense gravitational field will exert a strong influence on the object's path. Even a small change in trajectory caused by this encounter could reveal new information about the mass and structure of the nucleus. Jupiter's environment is very different from the rest of the solar system. The planet has an enormous magnetosphere filled with energetic charged particles. If the gas and dust around 3I Atlas interact with these particles, astronomers may detect changes in the comet's tail or new emissions. Such effects could reveal important clues about the composition of the material. At the same time, telescopes around the world will be watching closely. Scientists will track the object's position before and after the encounter to refine its orbit. Spectroscopic instruments will continue analyzing the gas cloud, while high-resolution images may reveal new jets or dust structures that were previously too faint to see. For now, the new isotope anomaly has only deepened the puzzle. The unusual chemical signatures suggest an origin in a cold and ancient part of the Milky Way, yet explaining how such an object formed and traveled here remains difficult. As March 16 approaches, astronomers see the Jupiter encounter as a crucial moment. Whether 3I Atlas turns out to be an unusual but natural comet or something that challenges current theories of planetary formation, it has already reminded scientists that the galaxy still holds many surprises.